All right. Hello, hello, hello. Uh, this is the first video for Unit 4. So in this, I'm going to be going through some subtle differences that you may not have picked up in Unit 3. And we're also going to talk about uh, a difference that hasn't been an issue yet because we haven't been dealing with anything other than atoms. So quick heads up. There is going to be a bit of a change moving forward. I am no longer going to be providing hard copies of the notes because we're seeing a push for us to have you guys doing more writing. So for now, where that's going to be happening is you guys are going to be writing more of the notes on your own. So you're going to need paper more often for that, those of you who haven't already been writing the notes. And you're probably going to start seeing more essay questions and having more writing assignments in the class. So prepare yourself for that. But for now, we're just going to be writing out the notes. Now, what I would recommend you start with is by writing out this first section of notes. So we're doing the Unit 4 notes. We are going to start with an introduction, which is going to do a couple of comparisons. We're going to start with atoms versus elements. We're going to talk about a couple of things, and then we're going to do molecules versus compounds. I recommend, not require, but recommend that you write this stuff down first, stop here, and then write the rest of this. Because I'm probably going to mention a couple of things that you might want to jot down in the margins for this. So I want to give you guys time to do that. So pause this and write this stuff down. I'm going to zoom in a little bit because I'm looking at this and thinking that might be a little hard to read. So I'm going to zoom in, and once I've done that, you guys can pause this so that you can actually write this down. So one sec. Let's go with 150. Is that easier to read? Yeah, let's go to. Is that all still on the screen? Yeah. All right. So write this down, and then I'll lecture over this. So pause this now, and then I'll go over this. All right. I'm assuming that you have paused it, and you already have all these notes written down. Okay. So I want to make sure that you guys understand the difference between the term atom and the term element. Now, yes, in practice, they are functionally the same thing. There is a subtle difference, though, between them, and you need to know what that difference is for the first topic that we're going to be going through when we start counting. Okay, and some of you just instinctually have already recognized this. Some of you just haven't quite made the connection. So hopefully this will go pretty quick, and it won't take too long to kind of wrap your head around what's going on. So in order to be an atom, it just has to be some combination of protons, neutrons, and electrons. And if we're being completely honest, it doesn't really even have to have neutrons or electrons. If it's a single proton by itself, it's an atom. But the absence of a proton, it's not an atom. So it's really just, it has to have a proton. The number of neutrons and electrons are kind of irrelevant. Well, they're not irrelevant, but they don't have to be present for it to be an atom. Okay, whereas an element is a specific kind of atom. Okay, an element is an atom that has a specific number of protons. So the examples I've got here, if it has one proton, by definition, because this is how we define our elements, by definition, that has to be hydrogen. Because hydrogen means one proton. Helium is 2 protons. Lithium is 3. 7 protons is going to be nitrogen. And if it has 92 protons, that makes it uranium. The number of protons determines that element. But all of these elements are still atoms. Okay, so in this case, elements are subtypes of atoms. Okay, and in that respect, it doesn't matter. Who cares about this distinction? Well, it matters here. Okay, so H2O is a formula that I am willing to bet that pretty much every one of you have probably heard of before. It's the formula for water. Okay, but in this, when we start counting, that's the topic we're going to be doing next. When we are counting, the number of elements in this formula is 2. There are only 2 different elements, hydrogen and oxygen. But if I ask you for the number of atoms, well, there are 2 hydrogen atoms and 1 oxygen atom. So the total number of atoms is actually 3. So while there are 2 elements, the number of atoms is 3. So that's kind of where this becomes important, because as we start dealing with larger and larger molecules, the number of elements might be 3, and the number of atoms might be 40 or 50 or 80, depending on how complicated the formula is. So that's why I wanted to mention this. Okay, that's pretty much it for atoms and elements. I'm going to scroll down for molecules and compounds, let you write this down, and then I'll talk about that. All right, so pause this if you haven't already and get this stuff written down. And I'm going to assume that you've done that. Okay, so molecules versus compounds, this one is completely new material. Okay, so a molecule is just some combination of atoms. Okay, so any collection of atoms that are bonded together, that's a molecule. It could be 2 atoms of the same element or atoms of different elements. If it's multiple atoms, 2 or more, if they're bonded together, then that is a molecule. However, it is not necessarily a compound. In order to be a compound, there must be 2 different elements present. Okay? And again, this is an important distinction because of things called diatomics that we'll talk more about. I might go ahead and throw those in at the end here once we get through this. So, in order to be a compound, there have to be 2 different elements. So, a couple examples I've got here. Okay, I'm getting ahead of myself. All compounds are going to be molecules because if it's a compound, it has to have 2 different elements. That means, by definition, there are 2 atoms, at least 1 of each element. So that is a molecule. But just because it's a molecule doesn't make it a compound. Okay, so all compounds are molecules, but not all molecules are compounds. So here we have O2, H2, and Cl2. Those would be molecules because there are 2 or more atoms, 2 oxygens, 2 hydrogens, 2 chlorines, and these are 3 just very common ones. Another good example would be P4 or S8. Those are 2 more examples of what we call elementals. They are molecules, but they are not compounds because there's only 1 element present. There's not 2 or more. Okay, so down here we have 3 examples that are compounds. NaCl. Well, that's 1 sodium and 1 chlorine. So that's a molecule, or that's a molecule because there's 2 atoms, but it's also a compound because there's 2 different elements, sodium and chlorine. Okay, SO3, again, 2 different elements, so it's a compound. 3 oxygens and 1 sulfur, so it's more than 2 atoms, but it's 2 different elements. Okay, and then here's a big one here. NH43PO4. We'll talk about what all the parentheses mean later. But there are multiple elements here. There's multiple capital letters because capital letters are how you pick out how many elements there are. Here we have N and C. Those are both capital letters. Okay? That means there have to be 2 different elements. The A is lowercase. This is why way back on like the 3rd or 4th day of school, when you started working on your element symbols flashcards, we told you that first letter must be capitalized, but the second letter has to be lowercase. It's so that when you have chemical formulas, we can tell where one element ends and the next one begins. And, diatomics. Let me pause this and get diatomics up. Okay, so I've added stuff for diatomics. So again, pause, jot this down. This is still part of the introduction. It's not technically part of verses, but it'd be better to get it done here rather than waiting. So jot these down. Okay, so these diatomics are special elements. And one of the most special things about them is they are 90% of the molecules that are not compounds. It's because of these things. Okay, so these can't exist by themselves. So these will always have a subscript. I say they can't exist as individual atoms. So when you talk about oxygen, like the gas that we breathe in, oxygen, it's not an individual atom of oxygen that's free and floating around. It's actually O2 because it has to be bonded to something. It can't exist by itself. That atom has to attach to something. So in their pure forms, these all have 2's after them. Okay. Now there is an easy way to remember these. It's what I learned when I was in school. They called it the magic 7. Okay. If you look at the periodic table, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all are right here together, and they form a 7. Okay. However, there are only 6 of them here. The 7th one is that ever-present oddball annoyance, hydrogen, hanging out way on the other side of the periodic table because, hydrogen. So yeah, those are your 7 diatomics. They have to be bonded to something. It might be another atom of the same thing. Like, for example, I put my pen down, so I guess I'm going to use this. For example, it might be N2 or P. Well, that's a bad example because that's not a diatomic. Ozone is O3, but these would be examples of how these can't exist by themselves. You're never going to have a chemical equation where H is by itself. It has to be bonded to something. Usually, it has a 2. That's pretty much it for this video. I'm going to go ahead and pause this here. So if you need to go back through it and rewatch something, it's relatively short. Most of this information you can get just by reading the notes. So hopefully there wasn't anything life-changing in this. And I'm going to stop this, and I will see y'all next time.